So we're going to go ahead and finish up this section of the topic here with interference of two sources. This is going to be how we're going to start this. So we've done and we talked about interferences with crests and troughs aligning and what it happens, and now we got to kind of take that knowledge and do a good bit more with it. So let's first start by defining a couple things. The first thing is defining in phase. So waves that are in phase, basically what this means is the crests and the troughs, like the crests slash troughs, are generated at the same time. So if I have like two speakers, they're generating the same parts of the wave at the same time. And this can, probably usually happen when you have the same music playing out of both of them or something like that. That's in phase. The next thing is a nodal line. This one we're going to define as a line of points where there's only destructive interference. So a line, of course, of points, a line where only destructive, think of nodal at the end, it makes nothing, it's all destroyed, destructive interference occurs. Okay, so only destructive interference occurs. And then what we have is an antinodal line. So it's the exact opposite, except it's not a place where only constructive interference occurs. It's a place where we get maximum constructive interference. So this is maximum, or a line, sorry, it's a line of maximum constructive interference. So basically you get your maximum amplitudes there. Of course it's not always here because as the waves go through, but as the waves go through, of course it's not all, as a wave passes through, sometimes it's down at zero, it's at equilibrium, so it's not always at a maximum, but it's always it's always a type of constructive interference that makes this to give you your maximum amplitudes that you can possibly have. So those are our three things we need to talk about first: nodal, antinodal lines. And let's go ahead and make a version here. So let's say we have a speaker here and another speaker here. We don't have to go too far away. So each speaker is going to send out spherical sound waves. They're going to go like this all the way out, and the other one's going to send out the same spherical waves. We've got these two speakers that are in phase with each other. Sorry, my drawing's not great, but they're in phase. Okay, so in phase speakers here. And what's going to happen is if we look at a line right down the middle here, right between them, down the middle, every point on this line, every point there, is equidistant from both of these speakers. So I could look to here, and it's going to be the same distance away from here, up here, same thing. Same distance away. So that means that the sound waves are going to travel the exact same distance, and if they start off in phase, and then they travel the same distance, when they meet each other, they're always going to meet at the same time. Crests are going to meet crests, troughs are going to meet troughs. Equilibrium points are going to be equilibrium points. They're all going to match up the same. And what you will get here is an antinodal line. A line just like this, defined by that, an antinodal line. If you move off a little bit to the side, they're going to be, so like I go off this line just a little bit, so I'll do that in yellow or something. I move off this line just a little bit, and what's going to happen is they're not going to match up as perfectly. They're going to be a little bit off. This one has to travel a little bit further to get over here than this one does, and then as I keep moving a little bit over and over, I'll eventually reach a point where they totally destructively interfere. And in fact, there's a whole, basically a whole entire line of points. I'll do that in yellow. A whole line of points that where they interfere and destructively interfere the whole time, and that's a nodal point. And if you went through and looked at that distance to each point, that if you look at here, what's happening along this nodal line is the path length difference is this one travels a little bit smaller length than this one. And that extra little bit that this has to travel is equal to half of the wavelength of our sound. And that extra half a wavelength basically takes two waves. One wave that would be like this, and it takes the other one and it shifts it behind by half a wave, which means it's going to be like this. Okay? And when that happens, we're going to have crests meeting troughs, and it's going to ultimately just give you destructive interference. And this whole way along this nodal line, that's the case. Everywhere you go, it's like the same length, right? Except this one has to go that extra half a wavelength to meet up there. And it then is out of phase by half a wavelength. And so this whole line is where that's occurring. They have that path length difference, it's called. A path length difference of half a wavelength, and it's all destructive interference. Then you could keep moving over a little further, and you'll eventually reach a point. And in fact, you could go over, from any of these, and you could eventually reach a point where you get constructive interference again. This is where they would be off by one full wavelength, and you'd have this other line here. It's another one of these antinodal lines where you get all these constructive interferences, and the path length difference now over to this line is twice what it was over here for the nodal line. So it's a full wavelength of a difference of getting to that line. And if you went through and did this, what you'd find is you would go back and forth between constructive and destructive, and you'd have these nodal lines, antinodal lines, nodal lines, antinodal lines, and you would go back and forth between these in and out of phase as they went from constructive to destructive type interferences, right? So nodal, 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 and then, of course, antinodal lines, antinodal, antinodal. Remember the antinodals, so they basically have a path length difference. The difference in the path, the length of the path they had to follow, of n times lambda. So any integer, it's either off by 0, that would be the middle, or 1 wavelength, that'd be these first ones out here, or 2 wavelengths, or 3 or 4, or whatever. Path length difference of n lambda. The nodal points have a path length difference, right? So this had path length difference of that. This would be of n over 2 lambda. Now, you'd start with half a wavelength. And then, of course, if you went to 2 over 2, it'd be this. So you want 3 over 2. And so up here, n equals 1, 2, 3, and so on and so forth. Whereas down here, n equals 1, 3, 5, so on and so forth. So 3 halves, 1 half, 3 halves, 5 halves, things like that. 4 halves would just give you 2, and we'd back to this situation. So these two different ideas here will give you this kind of pattern of going in and out. You may have experienced this ever if you've been driving along, and what happens is maybe you stop next to a building, right? So here's a building, and your car is sitting here, and you get the radio, the radio signal comes in and bounces off and comes over here, and so this acts like another source from this source you had over here. And what can happen is you could end up where there's a path length difference of one of these half integer versions of this, and you would be on one of these nodal lines, and it would make your radio cut out. But if you pull up just a little bit, pull up a couple feet, then your radio comes back in because you get off of that nodal line and you're back to where you have the more constructive interference, and you can get your signal back. Okay, we'll come back and talk a little bit more about this. So let's go ahead and talk about diffraction next, because we're going to need that to in order to continue. Oops, in order to continue on. So the next part is, I need a darker color, diffraction. So diffraction, I basically like to define that as the bending of light that passes around a corner. So bending of light, or really any wave, a wave passing a corner. Or if you want to give it a little different, passing a corner or an obstacle, or a some sort of boundary or a slit. And we'll talk about, we'll show each one of these examples, but it's basically the bending of light that passes around a corner. So the first thing is, let's say I have a corner here. This is my corner, and I have waves coming in like this. And what happens is these ones up here, they keep going straight, but down here these bend, and you get this bending of light as it goes around a corner. If you want an example of this, it's probably something you've seen where you've got a door, and the door is slightly cracked open, and you have the light coming in, all right? And you have light coming in through the edge of the door, through the thin slit. If you look at the light coming out, it doesn't stay in this perfect straight line like that. If you look at it, what does it do? It fans out, and it gets bigger, right? And that's what you see through that little slit in the doorway, and that's that diffraction as the light fans out like that. If you put light through a slit instead of just a single one of these, here's our boundary, here's our other boundary, some sort of obstacle, you send your wave, again I keep saying light, but it could be any wave, it could be sound waves or ocean waves, and it'll diffract out like that and spread out. Okay, so that's the first thing. We need to know what diffraction is. Now we can use this to do what is called the double slit experiment. In fact, I believe it's Young's double slit experiment. And this was first done with light. And so what you need is a source of light that is in phase and all the same wavelength, like we could do with the speakers pretty easily. But it's a lot harder to get a light that is like that. And that kind of light is called coherent light. Okay? That's light that is monochromatic. And chromatic, you should know, is like color, and mono is one color. So it's light that's all the same wavelength and in phase. It has to be this so that we can get this interference to occur, because we're going to be searching for an interference with this, and you need that. One of the only ways to really produce this is laser light. Any other kind of lights you have, it's not going to be monochromatic, like from regular light bulbs or flashlights, or even ones that are try to be of one color, because there's so many little fluctuations in the electronics and everything that it's going to give you all, still a big range of wavelengths, and it's not going to be in phase. It's all going to be kind of fluctuating and changing a whole bunch. So you don't want that. We want coherent light. We don't want light that's just all over the place like regular light would be. We want coherent light that's all in phase, all with the same wavelength. And lasers really do that for you. It's not important to know how a laser works, but lasers do produce that kind of light. So they're the best for this situation. So now that we have our laser light, we have our coherent source of light, what we're going to do is the double slit experiment. So up above we talked about one single slit. We're going to make two slits this time. And what we're going to do is we're going to send this light in. All right, here comes the light. And we're going to let the light go through, and it's going to fan out. It's going to diffract on both sides. And what's going to happen is the light from both sides then is going to actually come back and interfere. And so you're going to get those nodal and antinodal lines. And then far away over here, what we're going to do is put a screen. And on this screen, this light's going to shine all the way over to the screen. I know I didn't draw it going that far. But we're going to end up, as this light comes through like this, we're going to end up with these nodal lines and antinodal lines. And what they're going to do is they're going to make, in the very middle, they're going to make a bright spot. because that's right halfway between them. They're going to make this bright spot. Then you're going to move over and you're going to hit an antinodal line, and it's going to be a dark spot where their path length difference is a half. Then it's going to go back and you're going to get another bright spot where you're on the antinodal line, and then a dark spot on the nodal line, then an antinodal line, and it's going to go back and forth, and you're going to get this alternating pattern of light and dark lines. So you might expect, before you did this, that you're just going to get two big bright spots here and here from the two holes, but you don't. You get a whole bunches of them, bunches of these little interference lines, they're called, and it's because the light coming down the middle, right? The light straight down the middle has the same path length difference from this one to this one. And so it's always constructive interference, and you're always going to get a bright spot. But if you move up a little bit, what's going to happen is you're going to reach that point where the one in the bottom has to travel half a wave further than the one on top, and it's going to go back to dark. Move up a little further, then the one on the bottom has to travel a full wave further, and they're back to being in phase and it's constructive. And then so forth. Here's 1.5 waves further, destructive. 2 wavelengths further, constructive. All the way up. And then the same thing down. And so you get this kind of pattern. This was actually the first experiment that really showed that light acted like a wave, that it had wave-like properties. It gave this interference pattern like we saw up above that we saw here. So if we had put like speakers all along here, like, or if you walked along a line like this, you'd be able to hear it, wouldn't be able to hear it, be able to hear it, wouldn't be able to hear it, not hear it, hear it, not hear it. And so you'd have like, you know, this would be like the bright spots, the dark spots, the bright spots, the dark spots. So it's very similar to that, and it showed that light was acting like a wave. Okay, so we want to be able to look at this and do this mathematically. So first, we want to go ahead and define some terms on it. So the length I have a little issue there. Oh, I see why. I'm not having an issue, I just picked the wrong color. So we're going to go ahead and define this distance to be a capital D. Okay. We're going to define how far up we go, and we're not going to go very far, but we'll go to the first fringe. We're going to define that as S. We're going to find the distance between the slits as a lowercase d. And then we want to go under the assumption that D, the distance to the screen, is much, much bigger than the distance between the slits. And this is going to allow us to make a couple of approximations so that we can better do this problem. So if we look at this, here's our central line, and then we have a line going up, so this will be our little dotted line that goes to this little first maximum there. And this angle in there we're going to call theta. Okay? Then we're going to zoom in right here on this little spot here. We're going to zoom in. Here it is right there, this spot blown up. And we've got our two slits. Here's our two slits. And the light coming from here is going to be basically traveling parallel. This is one of those approximations I was talking about. If we are, got that little extra bit there. If this is really far away, like if I drew these lines in here, then if we're looking on a smaller scale, these are basically parallel. So that if I draw a line from here to here, such that it makes this a right angle, that makes this angle here theta, the same theta as this theta. We can approximate this to a right angle. And then what we want to get constructive interference is we want this little bit here. This is the extra distance that the bottom slit has to travel. It has to be equal to some integer multiple of lambda. It either has to be the difference of 0, in case n is 0, or 1 times the wavelength, or 2 times the wavelength, 3 times the wavelength, and we'll get that constructive interference. So we want this to be n lambda. And then again, this little part here, this part of the triangle, this over here is d, which is the hypotenuse. So that allows us to go ahead and write here, using this one, that the sine of this angle is about equal to the opposite side, n lambda over d. Okay? And then if we go back to this dotted line triangle here, If you notice something like, and I'm going to try and draw it a little better, it may not work. I'm going to redraw that triangle. We want this to be a really, really long triangle with a very small angle, okay, compared to how far it is. This down here is D, this here is S, and that's this dotted line triangle right here, okay? And if we look at that, this tells us that tangent of theta, because this is theta, is equal to S over D. And we can go under the approximation, if D is really big, if it's very far away, and this is a small enough angle, we can basically say that the hypotenuse here, if you look at the length of this hypotenuse, it's about the same as the length of this leg, given that S is sufficiently short, so this is a really small angle. And that allows us to say that this side is, it's a little bigger, but not much bigger. It's approximately D, which means that this tangent of this angle, which was opposite over the adjacent, is approximately equal to the sine of the angle, which is the opposite over the hypotenuse. Which means we can rewrite this as sine of theta is approximately equal to S over D. So I know we made a couple approximations. One, these two waves, these two light rays, D is so far away that these two light rays are basically parallel to each other, allowed us to make this triangle. And the second, it's so far away that the distance D is equal to the hypotenuse of this little triangle here, so that tangent of theta and sine of theta are about equal. So now what we have is the sine of theta equals S over D, and sine of theta equals in lambda over little d, and we can go ahead and rewrite this now as our rule, that S over D is equal to n lambda over D, little d. So that's the distance to the screen, the slit separation, the wavelength, and then what integer multiple you're looking at. You can do a little quick rearranging to get that the distance up, how far up do you have to move from the center of the screen to get to the first bright fringe, is then equal to n d lambda over S. Now not over S, over D, little d. Now the further you get up here, this gets to be a little less true because you don't have a small angle anymore, but for the smaller angles, the first few fringes, it's probably pretty close. In your data booklet, you're just given this version, d lambda over little d, and it's just the distance to the first bright fringe, literally the distance up the screen S. And that's to the first bright fringe, not the central bright fringe, but the first bright fringe. So this is the central, and I'm calling this one the first bright fringe. Okay, and that gets you all the way up to our nice little interference pattern and a nice little equation for figuring it out. Now you could go through and do the same thing with n over 2, right? If I went through and said this was n over 2, and I only allowed odd values of n, 1, 3, 5, I'd get the half integer versions. This would become n over 2, it'd put a 2 there, and you'd put a 2 in the denominator here and stuff. And so you'd end up with getting that that would give us the dark fringes, the half integer ones, that they are right in between the two of them. So if you want to find a dark fringe, it's basically, if this is, 1 millimeter up to this one, it's half a millimeter up to the dark fringe. Okay? It just cuts in half. You're just doing the same exact thing, but with an over 2 in it. All right, so now let's go back for a moment to diffraction. Okay? I'm going to go back to diffraction before we get back to using it. So let's go back to diffraction. And here we need to talk about Huygens, I believe it's pronounced Huygens, principle. And the idea is that any wave front you're looking at is comprised of an infinite number of spherical wave fronts, all interfering with each other and canceling each other out. Again, an infinite number of them, I can't draw them all canceling out except right along their frontmost border. right along those frontmost borders. Everywhere else they're canceling out all behind here, except along that frontmost border where you then end up with that wave front. So that's the front of any wave, even a curved wave. Uh, it's a bunch of these spherical waves all adding themselves up, canceling out everywhere except along the front edge of the wave. And this is basically a principle that's supposed to, explain diffraction and how it works. And so, for example, let's say we had our wave fronts coming in, right? And they hit this, they hit an object that's in the way. Well, what's going to happen? Well, normally it's all of these spherical wave fronts the whole way down, and they're all canceling out with each other. But then what we end up with is only this part. These bottom ones get blocked and cut off. So if you look at the bottommost wavefront, it no longer has anything canceling out the bottom half of it, and it can be the little curved wavefront. And so you end up with something like this that then goes out spherically and diffracts, right? So it's like flat wave and then it curves because there's nothing canceling out the bottom side of that curved wave. And this allows us to explain the diffraction of things. So for example, if we have a very wide slit, we have this come through, and then you get a little bit of bending out on the edge. It's mostly flat through here because that's not really affected, and then a little bit of fringing on the end, and it doesn't make a huge difference, and it diffracts out a little bit. If you have a very small opening, right, a very small opening, wave comes through, you're going to get a very large amount, a very wide diffraction occurring, much more than this kind of narrower version here. It's going to spread out. So the smaller this gets, the wider that spreads out. And the same thing with obstacles. You can have an obstacle and you can have this coming in, and then it'll bend kind of around the obstacle like that, and it can create this kind of ripple shadow. If your object, small, then you end up really having no effect on the wave. The wave just kind of only barely slightly notices, and it doesn't have much of an impact. So the biggest impact an obstacle or a slit or a hole or something will have is when the wavelength of the object is approximately equal to whatever the width of this is. So this would be like the width of the obstacle, and when they're about equal, that's going to be your largest impact. Okay, so if you think about think about like cracking a door open, a tiny small little crack will cause more spreading than when the door is all the way open. The light just looks like it comes straight in. So kind of think about that. So now I want to talk about doing this with single slit. So we talked about this double slit diffraction up here where we have the light and dark fringes, but now we have the same kind of spreading from a single slit like this. So if we think about this, reached the bottom of my little page there. If I have a single slit, right, what's going to happen is I'm going to get spreading from both sides, right? This light's going to spread out like this from this edge and from this edge. And so what you actually end up getting is over here, you don't get just just some large shadow, single shadow of whatever this is. You actually, so if you're slit, you're going to get a shadow wider than your slit. So as this spreads out like this, you don't end up with just one single big bright spot from your one single hole. What you actually end up with is the light coming from this edge and this edge actually interfere. And you end up getting an interference pattern where you end up with this really bright spot in the middle and then these smaller, bright spots over here, like that, and it kind of trails off. And if we looked at and said that the width of this one, let's say the width of this bright spot, let's call it, we'll just go with W again. No, I don't want to use W because I use W. Let's call it Uh-oh, I don't know, I've run out of an idea for let's just call it X, I guess. So if we call this the width of these little ones, these are all, how wide these little bright spots are all X. This one would be 2X, be about 2X, about twice as wide as these other ones, and it's much brighter, but there are some other little fringing effects. For this topic here, this is about the extension. You just need to know this basic shape. Later on in the more advanced topics we're going to have to do where you're going to have to actually know how to calculate this shape and everything. But here, you don't have to. Kind of calculate it kind of like we do with the double slit. But now this has an impact on the double slit. Because if we go back to the double slit, what you basically have is the interference of two single slits. So if these double slits are really close together, what you have happening is you end up with the single slit pattern from the first one, from one of the slits, right? I'm drawing it kind of lightly. And then you have the single slit pattern from the other one right next to it. And there, again, you need your screen to be so far away, and you need your slits to be so close together that these two almost coincide with each other. They're almost practically right on top of each other. And it creates essentially the double slit interference pattern has the double slit interference and the single slit interference. So when we go back up here, we talked about the light and dark bands. So how intense are these light and dark bands? Here's the central one. It's going to be the brightest one. It's definitely the brightest one, and it's this bright, thin central fringe like this. And then the next fringe isn't as bright because it's stuck inside the interference of the single slits. And then it goes down and it goes to almost nothing. But then there's that pickup in the single slit, and it goes back up and it goes up. And so basically what you have is this interference pattern inside another interference pattern. And your double slit interference pattern will look like this red one that I'm drawing, where you can see it's like the single slit is this envelope over top of it, where these peaks go up and then down and then back up and then back down, because it's really both the interferences, the single slit interference and the double slit. So this red one is what you would see, the double slit interference. What it would look like that, going up and down. Okay? This is what the single slit looks like. This is like the double slit looks like. You wouldn't see, of course, the green line. It would be the red one. And it's those two right on top of each other. All right, I think that's pretty much everything for this, and that's it till the next video.